Hello everyone, my name is Mubin Mahmood and I'm a PhD student at McGill University. Today I will present our accepted paper in VTC Fall 2022, which is titled as PSO-Based Joint UAV Positioning and Hybrid Precoding in UAV-Assisted Massive MIMO System. This is the brief outline of my presentation. So I will start with the UAV introduction, followed by the research motivation. Then I will discuss the system and channel model with the proposed joint hybrid precoding and UAV deployment optimization. Then I'll discuss the illustrated results and conclude the presentation. So the unmanned aerial vehicles, they have gained significant importance because of their high mobility. So the UAV is a simple aircraft, balloon, or drone, and it can be remotely controlled or it can be pre-programmed. And we have seen there is a growing interest, and some of the recent projects, for example, from Google and Facebook, they consider the global network coverage using the UAVs. Similarly, we have also seen SpaceX using UAVs for the Mars exploration. So the UAVs, they can be used for applications including military, search and rescue, as well as the telecommunication. So when it comes to the wireless communication, the UAVs, they can be used to extend the coverage area of a base station, or they can be used where there is a malfunctioning base station or there is an emergency situation. So the UAVs can be incorporated into the existing infrastructure and they can extend the coverage area. Also, they can be used to relay the information to some obscure places where there is no direct communication possible. So all of these things are possible because the UAVs, they offer the advantages of low cost, rapid deployment, and the increased possibility of line of sight. Massive MIMO, we already know, is the arrangement of large number of the antenna elements at the base station. And by increasing the antennas, we can increase the beamforming gain, and we can support a large number of the users by reducing the multi-user interference. Why millimeter wave communication? Because the 5G 3GPP has divided two main frequency bands for the 5G, which are referred as FR1 and FR2. FR1 is on the lower side of the frequencies and FR2 is on the higher side. And with millimeter wave, we typically refer to the frequencies in the range of 30 to 300 gigahertz. So with the increased frequency, we can actually get a high bandwidth, which can increase the number of the antenna elements that we can use in the given space. And we can also increase the data throughput. One such example we can see here in figure 5, for example, where there is a user supported by this base station. It has a throughput X. It is operated at 2 gigahertz with 2x4 MIMO. And if we increase the frequency from 2 to 4, we can see there is a 3.4 times increase in the throughput. But if we increase both the frequency and the size of the array, so we can see that from the original X, it can go up approximately up to 14 times of the original throughput. So this shows that the combination of both millimeter wave and the massive MIMO can offer us increased benefits. Here I just present the standardization progress towards the UAV communication. So recently 3GPP has signified some UAV communication network standardization in these releases. So I will not go into the detail of these ones. So this brings us to the comparison of the two communication systems, one with the UAVs and one without the UAVs. So without the UAV, it could be fixed and static, which means that if we want to we want to extend the coverage area, then we may need to deploy another base station. But with the UAV, we can just simply move the UAV from one location to another location. So these are short-term and temporary deployment, and these are highly mobile. So given all these benefits, there are some significant challenges which arises by using the UAV-assisted massive MIMO systems. For example, when we consider the number of the antenna elements, then UAVs, they have limited space, and then the array configuration becomes very important. Also, UAVs have limited power, so the use of low-resolution components to have high energy efficiency, it becomes a challenging aspect. Similarly, how to reduce the interference among the users, and also if there are multiple UAVs, then interference management becomes important. Also, channel modeling, because right now we have aerial to ground and aerial to aerial links. So channel modeling, it becomes an interesting aspect. Finally, the UAV deployment and the path planning, they can also impact the overall performance. So what is the motivation for this research? We saw that the UAVs, they can extend the coverage area, and thus they are a preferred choice for the millimeter wave communication. So in this research, we try to address the following problems. We try to see how a different array structure other than the uniform rectangular array, which is the most common array structure, it can be used for the future applications where we use UAVs. Also, how we can increase the spectral and the energy efficiency through some effective precoding schemes, and finally, how the UAV deployment, how the UAV location can impact the overall performance. Now I will discuss the system and channel model. So we consider a base station which is far located from these users, and there is no direct communication possible. There is a UAV which is relaying the information from this base station to this group of users. We consider the UAV has n antenna elements, and these users, we consider we have k users with single antenna elements. Then the signal which is received by the kth user is the combination of the desired signal, the interference signal, and the noise. And our objective here is to maximize the sum rate, which is the function of the signal to interference plus noise ratio. We can see that the optimization problem is highly challenging because of the constant modulus constraint, and also because of the UAV location. So X minimum, X maximum, they represent the boundaries within the flying space. Now I will discuss the channel model. So we use the 3D geometry-based millimeter wave channel model. The channel vector for the kth user, as given by equation 5, is the product of the fast varying path gain vector, which is already including the path loss. So the path loss, it is based on the 3D distance between the UAV and the user. And also it consists of the phase matrix AK, which depends on the user's angle location. So gamma K and gamma Y, these are representing the user's location based on the azimuth and the elevation angles. Now I will discuss the proposed joint hybrid precoding and UAV deployment optimization technique. So we consider the singular value decomposition for the hybrid precoding design. We consider the RF beamformer F and the multi-user baseband precoder W, which will reduce the multi-user interference and the number of RF chains. So for the RF stage design, we consider the SVT of the channel matrix, and for the baseband stage design, we consider based on the reduced size effective channel matrix using the regularized zero forcing. So for the RF beamformer design, we employ SVT as given by equation 8, where Q and V, they are the unitary matrices, and sigma represents the diagonal matrix. And to design the complete RF beamformer, for each RF beamformer per group, we design the RF beamformer using the phase angle of the entities of this unitary matrix V, as given by equation 10 and 11. So after formulating the phase matrix phi, we can calculate our RF beamformer for each group using the number of the RF chains we are employing for that group. After the RF beamformer design, we present the baseband precoder design based on the reduced dimensional effective channel matrix. So here the diagonal entities, they are the effective channel for each group, and the off-diagonal entities, they are the interference channels. And our objective here is to reduce the multi-user interference. So we use the regularized zero forcing. Here kappa, it represents the normalization factor, which is used to satisfy the power constraint. So after the design of the hybrid precoder, our optimization problem is given by equation 16. We can see that now it has satisfied the constraints C1 and C2, but C3 still exists. And this is still an NP hard because these optimization variables, they are jointly located in both the numerator and the denominator. So we employ particles from optimization based algorithmic solution. In PSO, there are different particles which are randomly placed in the search space. So they share their personal best solution, and based on that, the global best solution is updated. So here, the position of any particle I during the teeth iteration, it is given by equation 17. And after each iteration, the velocity and the position of the particle I is updated according to equation 18 and 19, where these are the optimization parameters. And our objective here is to maximize this sum rate. So after each iteration, each particle will update its personal best as well as the global best. So U here, it represents the location. So this is the proposed joint hybrid precoding design and UAV positioning algorithm. So I will not go into the details, but to briefly highlight, we first, based on some fixed UAV location, we formulate both the RF beamformer and the baseband precoder. And then we, using F and B, we calculate the optimized location. So we calculate both X naught and Y naught using the PSO. And after we find the optimized location, then we update our F and W using the same steps which we highlighted from 1 to 10. Now I will present the illustrative results. So here we consider 200 antenna elements, and we consider two different array configurations, which are referred as the uniform rectangular array and the hemispherical array. We consider 3 user groups, and each group having 4 antenna elements. We consider the UAV is located at a reasonably high height, which is 100 meters. So first we plot the sum rate versus the transmit power. Here we consider 3 different cases. The one without UAV, and then there are 2 cases with the UAVs. But for the 2 cases, we consider the UAV either randomly deployed or it is deployed using the proposed PSO algorithm. We also consider 2 different array configurations, HSA and the URA, and we can see that the UAV integration can increase the sum rate significantly. And also the UAVs which are deployed using the PSO, it can provide the higher performance than the random deployment of the UAV. Also, using the HSA can provide us additional gain of approximately 7 bits per second per hertz. Next, we compare the complexity of the proposed algorithm using PSO. So here we plot the sum rate for different number of the iterations for PSO, ranging from 1 to 100. We can see that by using even small iterations like 1 or 10, they can provide very high performance as compared to using 100 iterations. So the PSO, it is, in this case, is computationally very efficient. Next, we calculate the sum rate gain ratio, which is defined by using the ratio of the difference of the sum rate for random deployment or the PSO deployment versus the case when there is no UAV. And we can see that the UAVs, overall, the integration of UAVs provide the gain, but the gains, they increase significantly when we consider the PSO-based UAV deployment. Also, the HSA, which is the hemispherical array, it provides much better performance than the URA. Next, we calculate the energy efficiency, and we plot the energy efficiency versus the transmit power. Here, the energy efficiency is calculated as the ratio of the sum rate to the total power. And we can see that just like the sum rate, the energy efficiency, it provides much higher energy efficiency for the case when UAVs, they are deployed using the proposed PSO algorithm. Finally, we compare the trade-off between the energy efficiency and the spectral efficiency. And given the limited power for the UAVs, we can see that the proposed PSO-based algorithm can provide the highest trade-off between the energy efficiency and the spectral efficiency. This brings us to the end of the presentation. So here we presented the joint problem of the hybrid precoder design together with the UAV deployment. And we considered the SVD-based hybrid precoding, where RF beamformer is used to reduce the number of RF chain, and baseband precoder is used to reduce the multi-user interference. We used the PSO-based algorithm for the UAV deployment, and we saw that the UAV's integration can provide much better performance than the case when there is no UAV. Also, HSA can provide much better trade-off between SC and EE when compared to URA. This is the end of my presentation. Thank you very much.